All right, so we're looking at the Bernoulli distribution and binomial distribution today. Now, right. So we'll be looking at the binomial distribution and Bernoulli distribution. We start with the Bernoulli distribution. I want you to understand that the Bernoulli distribution is just a very simple form of the binomial distribution. Nonetheless, we need to look at the Bernoulli distribution first. So we're starting with the Bernoulli distribution. Don't forget, I said we are dealing with probability distributions, and the first one is, okay, we'll deal with the discrete distribution first. And so the first of the discrete distribution that we'll be looking at will be the Bernoulli distribution. All right, my whiteboard. So in the Bernoulli distribution, what happens, or what are we dealing with? We are looking at something here, and what is it that we are looking at? We are looking at an experiment being conducted, but just once. The whiteboard is loading. I will write on the whiteboard soon. An experiment is being conducted, but just once. And then we are looking at only two possible outcomes. And it could be any two things. For instance, male, female. It could be maybe go, no go. It could be, hello, can you hear me, please? I don't know if you're there.
We are here, sir.
We are here too, sir. So it could be go, no go. It could be male or female. It could be pass or fail. So we may use the word success or failure. Or, all right, so it could be group A, group B, but two things actually. And these two things must be mutually exclusive and exhaustive. What I mean is that, so that if you have, if somebody, maybe you have, let's assume 9 people. If 4 of them belong to a first class, then the remaining 5 must belong to the second class, maybe class B. 5 of them must belong to the next class. All right. I think that's just a big way, but let's start it afresh so that we can get it well. Now, this is what we're talking about. We're talking about the Bernoulli distribution. And the Bernoulli distribution, is such that, please, who is writing on the board, please? All right, the Bernoulli distribution is such that we have, number one, an experiment is conducted only once, conducted once, let's just use the word once. Number two, there are only two possible outcomes, e.g., male, female, pass and fail, go, and maybe no go. etc. All right, and we are interested. Okay, the random variable of interest is the number of success, number of successes. Okay. The okay. All right. Let's stop here for now. We may need to add a few other things later on. So these are what you should know about your Bernoulli distribution. Now, let's break them down. An experiment is conducted once. Let's assume that a man and a woman, I want to take an example of a man and a woman who want to give birth to just one child. That's an example of a Bernoulli distribution. Please, this young man is saying he can't see the whiteboard. Some of you can just help me help him? Okay, says, one line right says you can't see the whiteboard. Okay. So you can help him, please. Send something to him that will help him see the whiteboard. All right. And now, as we go on, the Bernoulli distribution. Okay, a male. I'm giving an example now. Let me not write it here. So let's do an example here. So consider the example of a man and his wife. A man and his wife want to give birth. Rukayat, what's the problem? Give birth to only one child. Rukayat.
Sorry, sir. I can't see the stuff you just laid down where you were trying to give a description about by. Sorry, I don't want to be last.
Can go through the previous boards. I have 2 boards, so you can check where you have a page or slide or whichever one is shown on your stuff there. Open it, just the way I'm doing on my stuff now, and then you can check the previous board. And you can come to the recent one, okay?
All right, okay. Sir. Thank you.
All right. So you can do that while I'm about what I'm doing. So now, an example, as I said before, of a Bernoulli distribution is a man and a woman who intend to give birth to just one child. Let's explain what that means. Now, if they are going to give birth to just one child, somebody may need to mute his or her microphone, please. If they are giving birth, hello. If they intend to give birth to just one child, then what will happen is that that one child may be a male or a female. Now, they may give birth to a female, let's call that F, or they may give birth to a male. Now, assuming that the man is interested in giving birth to a female. Okay, let's return back to what we were doing before. I believe you're going to understand this. Starting from the experiment is conducted once. In this case, actually, the man intends to give birth to just one child, the man and his wife. So it means that we're taking care of the experiment is conducted once. So the man and his wife want to give birth to just one child. I think I've written something like that before. Now, there are only 2 possible outcomes of this experiment. Look at what I said here the other time. There are only 2 possible outcomes. For instance, male and female. So they can either have a male or a female as their child. They cannot have, some of you will say, hermaphrodite. No. That's not the case. Male or female. You cannot have the 2. All right. And I don't think anybody has seen anybody who calls calls him or herself hermaphrodite before. So you either find a male or a female. All right. So in this case, that's it. And let's consider the other things too. We look at this now. So the random variable of interest is the number of successes. Now, it can either be that we are looking at the number of males or the number of females. So we may look at either of the two. But my concern here, we may use any of the two, but I will use the male. Now let's use the male. Assuming that we are interested, we can now say let X be the number of male, children given birth to. Now you understand something here. I know some of you may be thinking and saying, we said the experiment is conducted once, but what is the meaning of what we are talking about now? You're going to get that. Now, all right, so if X is the number of male children given birth to by this family, then we can define something here. I will not take us through the rigor of having to prove it to us. Don't forget, we talked about f of x, which we call small f of x, which we call our distribution, but this is a discrete distribution, so we use p of x instead. P of x now we define in this way. We could do some mathematical stuff to find out why it's that way, but for now, let's just take it the way it is. I'll write two different things that can be done, or rather, I'll write it in two different ways. Similar anyway, but just with respect to, they are different with respect to the letters I'll be using. So, oh, sorry, this should be 1. 1 minus x. Then x will take value from 0 to 1. All right. Now, that's the first way. I'll write it in another way. And that will be p raised to the power of x. 1 minus p. 1 minus p x equal to 0, 1. All right. And when it is written this way, if we say let q equal to 1 minus p, then p of x will become p raised to the power of x times q raised to the power of 1 minus p, and x will take values from 0 to 1. All right. Just give me a moment, please.
Oh.
All right.
Ezekiel, why do you always omit your mic?
All right, I'm in class. Now, please note that what we are doing will be going on air. Behave yourself, please. All right, thank you. Now, the probability of it will now be p of x q multiplied by 1 minus p, x equals to 0, 1. Okay, the reason why we have done this is, I have done this is because what you have here maybe what you may find in some textbooks, and in some other cases you may have this one, and in some other cases you may have it like this. So I don't want a situation where somebody will come and say, what I'm saying is a different thing. This is whichever one you are seeing of the two is correct. The only thing is that if you have it as in the one I put in red before, this one, then you must also take note of this, that the meaning of this Q is 1 minus P. All right, so that's that about that. Please take note of that. For those who are saying they cannot see the whiteboard, Ezekiel, go to, look at what I'm doing now, please. Click this place where you have page. I don't know if you can see my mouse there. When you click it, you should be able to see a whiteboard. If you cannot see the previous whiteboards, I think something is wrong somewhere anyway. But let me see what I can do. Somebody has Quadri.
Yes, sir. Yes, sir.
All right, so
yes, sir.
Let me again write so Bernoulli distribution.
The raised to power 1 minus P.
Don't worry about that. I'm coming back there. Bernoulli distribution, 36. All right. Now, what are the characteristics? That's what I want to look at now. I'll just leave it at 60. You can always zoom. Number one, the experiment is conducted once. Number two, there are only two possible outcomes, e.g., head or tail. Okay, let's use head and tail. Male and female, go and no go, etc. Number three, the experiment is conducted once. There are only two possible outcomes. The probability, okay, the random variable of interest is the number of successes observed. All right. I think we can stop here for now. So if there is any need to add something to it, we'll do that. All right. So these are the characteristics of your Bernoulli distribution. And as I said before, the Bernoulli distribution is a discrete distribution. Now let's go back. Don't know who had a question, who was trying to ask something concerning this, but it should not be P. It should be
X.
X, not P. Another was trying to raise that. Thank you. Okay, let's. All right, so it should be X. That's that. So I want to illustrate how to use what we have here now. Let's start with what actually do we mean by all that we have written here. I would like to start with, so I'm using this one now for now. This one. Now starting with this one, the first thing you need to know here is that we are saying the probability of X. And if you permit, sometimes we may prefer to just put Xi there. Just put Xi there, but let's leave the Xi thing out of it for now. If you permit, okay, this means probability, the probability of X. And since we have small letter x there, we could write it as probability of capital X equal to X. That's also a way to write it. Then instead of having this here, what I've written here could take the place of this. So in that case, whichever might be the case, we have this to be this, what we have here. So now X is 0, means that we may have no male child, or rather the man may have no male child with his wife, though they want to give birth once. So when the experiment is performed once, the man and his wife decide that they want to give birth to only one child. So she may be pregnant and give birth the first time, and they don't have a male. That means they have a female. That's the meaning of this 0 here. That's what it means. So if she gives birth and they have no male, it will be 0. But supposing she gives birth and they have one male, then it will be 1. All right. Just a moment, please. All right. So looking at this now, so if he decides to give birth to just one child and his wife becomes pregnant, he may have a female. That is the meaning of this 0. And he may have a male. That is the meaning of the 1 you are seeing here. So these are the possible values that a random variable can take, 0 or 1. And so when you have that, we are saying that there is a probability, and that probability, if you use theta, you may use theta, you may use p to represent it. But what we are saying is that there is a probability of success. The probability of success, if you are using the first equation I have, so let me write them, first equation 2, 3. If you are using the first equation, then the probability of success is theta here. And when theta is the probability of success, what that means, okay, what that means is that 1 minus theta would be the probability of failure. So you can get that here now. Theta is the probability maybe I should just type that to make things faster. Theta is the probability of success and 1 minus theta, can't put 0 there, so is the probability of failure. So let me remove the 0. I'll have to write theta there. So, permit me. All right. So 1 minus theta is the probability of failure, whereas theta itself is the probability of success. So probability of success, probability of failure. That's what we mean here. Now, but in a case where you use equation 2 or equation 3, it's similar, just the change in the letter. Then in that case, P, small letter p, please, not capital letter P. So is the probability of success while 1 minus P, 1 minus P is the probability of failure. All right. This is for the second case. Now for the last case, it's similar. The only thing is that we have reduced 1 minus p, or rather we have made q to become 1 minus p. So q will be the probability of failure in the third case. All right, so these are the cases that you can have. Make this a bit smaller. So in any case, you know you have a probability of success and a probability of failure. I'm taking the time to explain this so that you will not be confused. We're going to take an example or some examples on it now. Probability of success, probability of success, probability of success. No, not with the x's included actually, just the. All right, then probability of failure, the one is not included. Probability of failure, probability of failure, and then probability of failure here. So you have your choice to make, but I want you to just know that this one, in whichever choice you are making, do not use this one except you specify that q is equal to 1 minus p. So you will need to specify this one. If you are going to use the third one, you will need to specify this one. If you do not, then do not use it, because anyone may assume that q is something that you have not defined, I believe, but if you define q to be equals to 1 minus p, then you are fine. All right, for clarity, it's just very much okay if you use any of the other two. But if you use the third one, make sure you define your q to be 1 minus p. All right, that's it. So now let's take an example. The probability of success, there will be a need for there will be a need to give the probability of success if this question will be complete. But as long as this question is the way it is now, what we can do is what we have done. So supposing that somebody gave us further information. A man and his wife want to give back to only one child. Suppose, okay, let's put a full stop there. Suppose that I think it will be good for us to just have this question taken to the next slide, so we'll not have to make this rough. Next page, further. Right. So, a man and his wife want to give back to only one child. Suppose that the probability of giving back to, okay, of having a male child is 0. Actually we say they are equal likely. So we use 0.5, but there are situations where we may not, but we just usually assume that they are equal likely. But let's do it that way. And 0.5. So the question now, find the probability that he will have, or they will have, okay, they will have a male child in one trial. Now, I don't need to put this again, because sometimes when you see the word in one trial, you should already know that you have a Bernoulli distribution. But a man and his wife want to give back to only one child. So since there is the word only one child here, I don't need to put in one trial again. All right, so looking at that now, we want to solve this. And that should not be difficult if you understood the principles that we have used for the coin. The per coin stuff. You should be able to do this even without knowing the Bernoulli distribution. You should be able to find the probability that this will happen. But I'm going to solve it. Now look at this. In this case, we have been given a number of things. The first thing that we were given, the first information is that they want only one child. And that only one child thing that we have been given there shows us that it's a Bernoulli distribution. So definitely our P of X will be equal to, okay, I prefer to use theta here. Somebody will not confuse that with P here. Theta raised to the power of X, 1 raised to the power of, okay, 1 minus theta raised to the power of 1 minus X. When you are stating a probability distribution, you must make sure that you state both the distribution and the range of values for X, as I have done here. If not, your distribution is not completely stated. And that means you have not done justice to it. Okay, so where P, okay, not P now, there isn't theta. So where theta equals to 0.5, that's the probability of success. And mind you, according to what we're told here, suppose that find the probability that they will have a male child. So we are interested in having a male child here. We have been told that somehow, because we're saying find the probability of having a male child. So that means he's interested in the number of male children. So X is a variable that represents the number of male children. All right. So now we look at, but it's a Bernoulli distribution. So we are talking about just one male child. All right, so from there, we may now say probability. Permit me, you may write it this way, but I want to do something a bit different here. I talked about it before. X equal to X. So capital X is the random variable, small x is the value it takes. So the probability that X equal to 1 is the probability that he has a male child. And that will become, before we do that, let's still do something, one more thing. Probability of X, since theta is equal to 0.5, will now be 0.5 raised to the power of X multiplied by 1 minus 0.5, which will also give us 0.5, 1 minus 0.5, and that will give us 0.5 also. But since we did not look for that initially, we can just, okay, let's do something, make it a bit neater. Comma, theta, 1 minus theta, or we may say implies 1 minus theta equal to 1 minus 0.5 equal to 0.5. So in that case, we don't need to start doing the mathematics again. So we just need to put 0.5.
So what of the X? Can't we put 0?
So you can't put anything there yet. There are two values for X. So which of them are you going to use? Is it Quadri who asked the question? Hello?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
There are two values for X. So which of them are you going to put?
I'll put 0 first.
You can. That's not how to do it. Just calm down. Listen. You get it now. All right. So we're going to have 1 minus X. We don't need 0 in this case. But you may not understand. So let's just continue. You get it now. So I may come back and put my comma X equal to 0, comma 1. Now, actually, this is the distribution. This one, the first one, so that you be aware, the first one that we stated, everything here, is the general case for all Bernoulli distributions that you can think of. The general case, there's no particular P there, no particular P there, so it's a general case. But when we fixed theta to be 0.5, it gave us the specific case we're talking about, which is the case of this man and his wife. Do you get that? Do you get that?
Yes, sir. Yes, sir. Yes, sir.
Okay. So
No, sir. No, sir.
the general formula for any Bernoulli distribution is what I put in red here. And that's what we looked at in the previous page. Do you get that now? Do you understand that?
Yes, sir.
Okay, so that's what we have looked at there. But in order for us to solve the question that we are dealing with currently, we need to fix the parameters we got from the question into the equation that is for the general Bernoulli distribution. When we fix that parameter now, we have 0.5. Then we get the Bernoulli distribution that can help us answer our question here. So this Bernoulli distribution is specific to this question. Do you get that now?
Yes, sir.
Okay, the lady didn't answer again, but I'll continue. I will assume that you are thinking about it or you've gotten it. Probability of X equal to, the question said, find the probability that they will have a male child. Now we are already answering this question. That's why we have this Bernoulli distribution, this one here. That's what I meant. Now we are answering the question now. This is the distribution. We now want to use the distribution to predict whether we are going to have a male child. Like whether we are going to have, okay, we want to predict that we are going to have one male child. Look at the question again. A male child, a male child. So I told you the other time that X equals to 0 means that, as I said before, we will have probability of X equal to 1 in this case. Okay, why are we having it to be equal to 1? The reason is because the question said, find the probability that they will have a male child, a male child, a male child. And I said X equal to 0, 1, meaning that X can be, when they do it once, they give birth, the wife gives birth once, gives birth once, they may have no male child. That means 0. X is equals to 0. Or they may have one male child. That is X equals to 1. So when the experiment is performed once, don't mind me calling it an experiment in this case, actually, but in terms of statistics, that's what we call it. The possibilities are no male child or just one male child. Now, but our question says find the probability that they will have a male child. So we are going to put X equal to 1 here. And when we do that, we are now going to have 0.5 raised to the power of 1 multiplied by 0.5. Please, if you are writing on the board, please, you may need to, or you are sliding, please, you may need to pause. All right. 0.5. Now raise to the power of 1 minus 1. And at the end of everything, we are going to get 0.5 as our answer. Now that's because we are asking for the probability that they will have a male child. But assuming that the question did not stop there, perhaps the question said, find also the probability that they will have they will have a female, or perhaps they will not have a male. So if you don't have a female, if they don't have a male, that definitely they have a female. Now, so what does that mean? You need to know how to interpret your questions well. That means we'll be looking for the probability that X is equal to 0. And that's why I had to first find this. I told you that this what I've looked for, or what I've found here, this one, is specific to the question that is here. And how do I mean? So if you didn't get that now, you should get that now. Supposing that the probability that was given to us here was 0.8, then the question will change. This does not change. This remains the same for every Bernoulli distribution. All we need to do is just change theta here to 0.8. When we do that, it means this equation is no longer useful for this question. This equation will be put somewhere else. Then we'll just change this to 0.8. Then it becomes a new equation useful to answer this question. That's what I was trying to say. All right, so in continuation, we will have, if we are looking for the probability that they will have a female, then it will be the probability that X is equals to 0, and that will become 0.5 raised to the power of 0. X now is 0. Then 0.5, I'm dealing with this now, this part. 0.5 raised to the power of 1 minus 0. And wonderfully, this part will become 1. Don't forget that this one, although I jumped some stuff there, but you should understand that it's preferable to, let's finish it up. So equals to 0.5 multiplied by 0.5 raised to the power of 0. That will be 0.5 multiplied by 1. That will give us 0.5 as our final answer. All right. So that being said, we can move on to the next question. So we are dealing with a situation where they have a female instead. That will become 1 multiplied by 0.5. Since 0.5, 1 minus 0 will be 1, and that will give us 0.5. Now, you notice that we are getting 0.5 in each case. It's a very simple stuff. You do the experiment once, so the probability of success remains the probability of success, and probability of failure remains the probability of failure. Let me explain so that you get it. If the probability we're given here was 0.8, that means the probability of having a female if we're given 0.8 as our probability of success, assuming we had 0.8 here, then you find out that your final answer here would have been 0.8. Let me write with another. Would have been 0.8. And your answer here would have been 0.2. Note that it didn't change anything. It means that what you would have gotten as the probability of success will remain the probability of success, that's having a male, and the probability of a female will remain the probability of female, that means having no male child. Now, that is because this is a simple case. You are doing the experiment just once. Do you understand that, please? Do you understand
Yes,
that?
ma'am.
Yes, sir. Yes, sir. Yes, sir.
Right. So, one more interesting thing. We are done with that so it doesn't matter if you change the question, perhaps it's no longer male and female, perhaps it's just go, no go, or in class A, not in class A. You just need to interpret what we are talking about well. Note that it is also possible to find the probability of success if you are given, well, let's leave that. I think that's this is sufficient to talk about the Bernoulli distribution. Now, we can go on to the binomial distribution. Now, the Bernoulli distribution is very important. Very, very important to you. And okay. What is a binomial distribution? We want to look at that now. A binomial distribution is a series of Bernoulli distribution. What do I mean by that? In the case of a binomial distribution, you are not going to be performing the experiment once. You are going to be performing the experiment more than one time in order for it to be binomial. And as I said before, the Bernoulli experiment is a simple case of the binomial experiment. We're coming there. So if you call it Bernoulli distribution, the simple case of a binomial distribution, you are not wrong. You are not wrong. The reason is because the Bernoulli distribution is coming from the broad term that has to do with the binomial distribution, or the broader class of the broader class of distribution called the binomial distribution. Now, consider that man and his wife again. They want to give back this time, but they want to give back to, assuming they said, okay, no, we don't want one child. We want 4 children, for instance. Then what is going to happen is that they will be having to give, okay, now they will be having perhaps more than one male or more than one female, as the case may be. So let's take a closer look at it. Who is sliding on the board? Please help us, help us, help us. So now the binomial
Hello. Okay. I wanted to be sure that I'm still in the class.
You are. All right. So binomial distribution, can you see the board? Number 1.
Yes, sir.
All right. The random experiment. Can everybody stop doing something on the board? Can you just listen? Don't write on the board, please. Just listen, please. The random experiment now, the random experiment is performed at least. Now, because we want to put a distinction between the binomial and the Bernoulli distribution, we may use the word it is performed at least twice. Okay, but let me use the word more than once, but I will show us, okay? So if you like, you may use the word at least once, so that we can include the Bernoulli distribution to it. Let's leave that way. So that's the first one. So the next thing is that there are only 2 possible outcomes, and then the probability of success is P the variable, the random variable of interest. Okay, I think for the one I want to write in number 4 can come first before that one. The random variable of interest is the number of successes called X now. And the random, okay, the probability of success is P, and the probability, that is if you are using P anyway, of failure is 1 minus P. And then finally, the number of trials are, okay, each trial, maybe I should just write that this way. Each trial of the experiment is independent of the other. Now, what do we mean by this that we have here now? So we can start to look at. Number 1, the random experiment is performed at least once. So that means that is, sorry please, the experiment is performed n times. Now, we looked at the case of the Bernoulli distribution the other time, and we performed the experiment just one time. But now we want to perform the experiment n times. And when we perform it n times, we are looking for the number of success, which we are calling our X now. And then we are also looking at the probability of failure and the probability of, okay, we are interested in the probability of success, P. So from which we get the probability of failure, which is 1 minus P. And each trial of the experiment is independent. So the binomial distribution may be looked or may be seen as what we may call the repeated Bernoulli distribution. So each of them is a Bernoulli distribution. So just the way we said before, but since we are conducting the experiment n times, we are going to have a binomial distribution. So a series of Bernoulli distributions. That's what it means. All right. I want to put some things here. I want to add some things here which you should take note of. The probability of success is P here also, and the probability of failure is 1 minus P, small letter P. And then, okay, I think that's sufficient for now. Okay, now returning back to the binomial distribution, we can now obtain, okay, let's do an example. Let's see what we're able to get. But before then, all right, writing the PDF now may not really be something that you want to look at. Okay, let's look at this now. That man we talked about earlier wants to give back to 4 children. Okay, let's say 5 children. 5 children. Suppose that the probability of having a male child is 0.5. Find the probability that they will have 2 male children. Okay, let's take it. Let's put it at 3 male children. Now, note something. In this case, the man can have more than one male child. Is that true? Is that true?
Yes, sir.
If they want to give birth to 5 children, then they can have more than one male children. Is that true?
Yes, sir.
Okay, that's true because if they give birth to the first one, it may be a male, maybe a female. So assuming that they give birth to, it's possible that they can have. So let's look at what we are going to have here. The distribution, we can look at the distribution, but I will not be writing that here. That's an example. The distribution will look something like this. So sorry. F of x equal to n combination x. And for some of you, you already know that we may write it like this, n combination x, if you like. It's the same thing. Probability of, success now raised to the power of x, then 1 minus the probability of success raised to the power of n minus x, and comma. This time around, x can take every possible value you can think of within the boundaries of 0 and n. So look at this now. 0 and n inclusive. So 0, 1, it continues until the total number of trials that you have there. Now, so dot, comma, n. Please, do you get this distribution? Let me explain. Now, because we are performing the experiment more than once, that is the reason why you are having n combination x. From your combinatorial analysis, you have something like this. So it means that there are ways to choose the way they give birth to the male children. So this one takes care of that. Then the probability of success is this. And so that if you are repeating it maybe once or twice, that's why x is coming here. You don't need to really understand that, or you may not understand that, but if you do, it's a plus to you. But if you don't worry about that. But just understand that this n combination x is coming because there are a number of ways by which we can choose the children. All right. And this one is the probability of failure. So it may be repeated depending on the value of n and x. So probability of success may be repeated depending on the value of x. All right. So the only difference here, if you have noticed, I don't know if you have noticed that the only difference here between the Bernoulli and the binomial distribution is n combination x. And perhaps the fact that you have more values here. How many of you have noticed that? Hello? Hello?
Yes, sir.
So those are all right. So those are the differences that you have. Or rather, those are the differences, this one and this one. So other than those differences, they are the same. But note something, that just the way we have it now, if our n was 1, that means we perform the experiment once, then what we will have is n combination, 1 combination 0 or 1 combination 1. Because if our experiment was performed once, then we only have 0 and 1. And in either case, 1 combination 0 or 1 combination 1, you still get 1. So it becomes Bernoulli distribution. That is when the experiment is performed only once. Do you understand that?
Yes, sir.
All right.
There's also difference, which is 1 minus 2 per n minus x instead of 1 minus x.
Yes, thank you for that. But I just said that if our n is 1, that's what I said. So n will have to be 1. If n is already 1, I have cycled this out. The n will become 1 because n is 1 already. That's what I said. So do you understand the young man who asked that now, or who said that?
Yes, sir.
So if our n is already 1, in which case we are already putting 1 here, definitely this will change to 1. So that's not a problem. So the difference between the two of them is, okay, all those things we just talked about. I understand what that man is trying to say, and I've captured it in my statement now, even if I didn't capture it before. So that's that about that. So in any case, once n is 1, the binomial distribution becomes Bernoulli immediately. All right, so that's why I said the Bernoulli distribution is a simple case of the Bernoulli distribution is a simple case of the binomial distribution. All right, so in continuation, let's look at our example that we're looking at. Now the man wants to give back, and we have just seen that. I think it will make sense just copy the equation rather than having to write it again. Okay. So now this is the equation. We are actually solving the question now. And make this a bit smaller. Now, this is the general formula for, or rather the general specification of the distribution for the binomial when it is binomial. Now, but we want to solve this question. From what we are given, we see that n is 5 because we were told that the man and his wife want to give birth to only 5 children. And not something, it is in such a way that if you don't give birth to one, you cannot give birth to another. We are assuming here that they will not give birth to, okay, even if they give birth to twins, well, but we are assuming that they will not give birth to twins. Do we get that, please? Hello?
Hi, sir.
Okay. But even if they give birth to twins, now listen to me carefully, even if they give birth to twins, it's still captured because the two children cannot come out at the same time. Do we get that? So that if they give birth to the first child comes out, we will know the gender, and perhaps the midwife discovered that, or the nurse discovered that there is still another child, and so the child will come out, and even if they had done a scan, they knew that she's expecting a set of twins. They'll bring the child. The first one comes out, we determine the gender before the second one comes out. So the trials are independent. That's what we mean by the trials are independent. So one trial does not depend on the other one. So if a child comes out here, we determine the gender. We check again if there's another child, even if they are twins. But if there's no twins, you have to wait for another 9 months before another child will come. All right, now a man and his wife, and even if they are triplets, it still covers for it, even if they are 4 children. But we are saying that they want to have 5 children. So each time there's an experiment. Now, only 5 children, so n is 5. Suppose that the probability of having a male child is 0.5. That means that P will be 0.5. And our 1 minus P will be 1 minus 0.5. And that will give us 0.5 again. All right. And that means that okay, we're not done. Okay, we are done for concerning what we need to specify our distribution, we are done. So we can now have f of x so I used f of x. We're supposed to use p of x. Don't forget that we are using f of x for the continuous random variable. So permit me, small p of x capital X equal to small x. As I've been saying, X is the random variable. Capital X is the random variable, I mean, while the small x is the specific value that the random variable takes. That's why you're saying X here, X here. Now, so from our question, we were told to find the probability that he'll give birth to 3 males. So, probability that they will have 3 male children. So because of this, we are going to look for the probability that X is equals to 3. And that will give us 3 combination. Oh, before that, we need to find probability that X equals to X with the parameters that we have there. So we are going to have 5 combination X. I'm fixing the parameters into this equation now. Probability, okay, P is 0.5 this time around. So we get 0.5 raised to the power of X. And then we have 1 minus 0.5, which we have found to be 0.5. I mean 1 minus P, which is 1 minus 0.5 and 0.5. Then we have 5 itself minus X. And then X takes value from 0 to, since N is 5, it will take values from 0 to 5. 1, comma, you should specify all of this because it's just, we're having just a few digits. It's just 5, so it's not going to be long. 0 to 5. Now, having done that, we now have probability that X equals to, capital X equals to 3. Now to become this, so substitute 3 anywhere we see X, we have 5 combination 3 multiplied by 0.5 raised to the power of 3 multiplied by 0.5 raised to the power of 5 minus 3, and you don't need to specify all of that again. So it will now become 5 combination 3. That should be, what should that be again? 10, I suppose. You can look for it if you, okay, 5 factorial.
It's 10. 10.
Okay. 3 factorial.
It's 10, sir.
2 factorial. So, all right. That's it. So anybody who cares to, so it says 10, I believe. So what next?
That will be 0.125.
All right. Let's do this. We can use the law of indices. I don't want to do a lot of calculations here. So let's just use the law of indices. This will go away with this. Okay. This will be 3.
So that will be
plus 5 minus 3. Okay. So minus 3 will cancel 3. And that will become 0.5 raised to the power of 5. All right. You were saying something, please.
Yes, I said 0.5 raised to power 3 plus 2, and that's 5. The same thing you have.
Okay. So, but for examples, if you have an assessment or something, you can do well to leave it like this. Then punch the remaining ones on the calculator. Whatever your calculator gives you. So you don't need to start. You said?
0.3125.
0.3125. Let me cross check that. Because some of you in the class will just listen to, or might just listen to it and not go to cross check. So at the end of the day, it may not be, or you may get to the class, go back and 0.5. Right. So that gives 0.3125. So that's that about that. So that's the final answer here. But there are also other possibilities. You may be asked to find the probability that you give birth to 2 children, 2 male, no male, 5, even 5 males. So you can find probability that x is equals to 0, x equals to 1, x equals to 2, x equals to 3, x equals to 4, and even to 5. And then you can put your answer here. The reason why I'm saying this is because you need to be aware of what we are doing. Okay, let me add one more example to this. Now, in that case, I will need to change this question a bit. Okay. Now, find the probability that they will have at least 2 female. We are interested in the number of males, so just use male. 2 male, but not something. The expressions are kind of converse. Or should I use the word? Well, somehow you can, let me say it this way, you can imply one from the other. Just look at this now. One can be, it may be implicit. For instance, if I said, the question I wanted to ask was, find the probability that they have 2 males. I want at least 2 males, but let's look at it this way. If I say find the probability that they have at least 2 females, what does this mean? Please, can somebody tell me, find the probability that they have at least 2 females. Note that we are interested in the number of males, actually, but supposing now, the reason why I've added this to our equation, or rather to the question, is because I want to put something that looks confounding here, something that at least maybe pushes you a little bit. Now, if I did not write this, maybe I wrote 2 males, at least 2 males, then I will have no need to write this. Because all I've been talking about now are male, the males. Now, and I have find the probability that they will have at least 2 females. Logically, you should understand that what this implies, since they're interested in number of males, what this implies is that they are looking for, you are looking for, in this case, number 2, you are looking for the probability that they will have, if they have at least 2 females, that means they have 0 or 1 male. Do you understand that, please?
Yes, sir.
So that means, this means that probability that they have at most 1 male. So you need to think logically by yourself and transfer it to male, because we were told that we're interested in the number of male children, males. So if you see something like this, then you say, they said 3 male here, but you said we are interested in the number of males, and now you're asking that I find the probability that we have at least 2 females. How do we do that? If you go and then you put at least two, because I'm going to do something on that now, and you put 2 there, it will be wrong. But if you change it, because you have females here, if you change it to males, then you'll be correct. That will mean at most 1 male. All right, I'm not going to ask the question this way, but I'm just doing it this way so that you can understand what we are doing. So let's go back to what we said. I may come back to this later on. So at least 2 males. Since I've been talking about male, I don't need to specify that we are interested in the number of males. You should already know. That's why I did not put anything like that here. But in a case where you have it the way I said just now, you should be very careful to see that you don't mix them up. All right. Now, I want to do the second one. Now, we are looking for the probability that you will have at least 2 males. Now, don't forget that our distribution is what we have here. So, 2 males. Sorry, please. So this is our distribution. And since we already have this distribution, we just need to find, we are looking for the probability of at least 2 males. Now, what does that mean? The probability, if you remember when we were dealing with cumulative density function, that was what we were looking for. We are looking for the probability that x is greater than or equal to 2. That's what we mean by at least 2 males. Do you get that, please?
Yes, sir.
Okay.
Yes, sir.
Probability that, so what do we mean? You can have 2 males, can have 3 males, can have 4 males, can have 5 males. That's what we mean by at least. Somebody is doing something that is wrong to the board. Please refrain from that, please.
Juwera.
Please. All right. 2, 3, 4, 5. And that's the meaning of x is greater than or equal to 2. Now, but because you will need to compute this for 2, 3, 4, and 5, and somehow I think I like to make it shorter. You could actually just compute for 0 and 1, and then remove the result from 1. So if you do for, it's going to be shorter than if you do for all of this. And how do you intend to achieve that? How can we achieve that? We can achieve that by saying this that you have seen here is the same thing as 1 minus the probability. I told you that sometimes you may want to put, but let's leave it this way for now. You may want to put R here, probability. So to avoid confusions, we can leave it here this way, leave it like that for now. And it will be equal to 1 minus the probability that x is less than 2. It is also the same thing as the probability that x is less than or equal to 1. 1 minus the probability that x is less than or equal to 1. Anybody confused with these two statements that I have on the board? Anybody?
No, sir.
So x is less than 2 means that x can take values from 0 to 1. And x is less than or equal to 1 means that x can also take values from 0 to 1. So you can use any of the two. But I think it's preferable to make sure that 2 shows up there. Because if it is greater than or equal to 2, then definitely the reverse of it says that it is less than 2. So you can always learn it. Note that, please master it. Don't mix it up. Do not write it this way. If you do, you'll be wrong. Because as it is now, they are not mutually exclusive because 2 is included here, 2 is also included here. But if you do it this way, you are correct. It means 0 and 1 are here, whereas 2, 3, somebody is meddling with the board, please. 2, 3, 4, and 5 are here. All right, so looking at that, it means 2, 3, and 2, 3, 4, and 5 are taken care of here. All right, so in that case, we can just do for 0 and 1, and then we remove it from 1. That will give us, because they are mutually exclusive now. If you remember your probability stuff that we talked about, we said A plus A prime is equal to 1. Is that true? Is that true?
Yes, sir.
So this
Yes,
is
sir.
A. Assuming that this is A now, then this is A prime. Because it means that A will be equal to 1 minus A, the complement of A. So, and you know that anything that is not here has to be here. So that's what we are using. That's the principle we are using here. We can go on from here. Now, we will now need to find the probability that x is greater than 2. So probability that x is less than 2 will be equal to summation x takes value from 0 to 1. And then we are going to have 5 combination x multiplied by 0.5 raised to the power of x, 0.5 5 minus x. So which is what I've written here before, up here before, just this, only that there's a summation sign now because we need to do it for each one and then sum. So what are we going to do now? The first time, 5 combination 0, 0.5 raised to the power of 0, 0.5 raised to the power of 5 minus 0. That's the first one. We've done this for 0 now. Then we go plus. We are doing it for 1 now. 5 combination 1. 0.5 raised to the power of 1. 0.5 raised to the power of 5 minus 1. That will become 0, okay. This will be 1. 5 combination 0. Anything combination 0 is 1. This will also be 1. This will be 0.5 minus, so for now, let's leave it at 0.5 raised to the power of 5. Now for the next one, we are going to have 5 combination 1. That will give us 5. Anything combination 1 is that thing. So 5, 0.5, and then 0.5 raised to the power of 4. So if you have it to this level, you can use your calculator to find, so if you have the answer from your calculator, you can let me know. 0, so we have 1 multiplied 0.5 raised to the power of 5. That should be 0.0312. So 0.0313. I told you that you should use 4 decimal place when you're doing your calculations of this type. And then 5 times 0.5 times 0.5 raised to the power of 4. That gives 0.1563. So you can cross-check in case I'm wrong. All right, and that will give us 0.0313 plus 0.1563. So 0.0313, and that will give us 0.1876. Okay, so, but we are not done. We have only done a little part, just a small part of what we intend to do. So the probability that x is greater than, well, not a little part anyway, but we are not done either way. Will now be, so you may write therefore, will now be equal to 1 minus from here. So it will now be 1 minus 0. So if you like, you might have called this equation 1. I think I like to do it that way. I do, so that it can be neat. So you may just write from equation 1 0.1876, and that will be 1 minus 0.1876, and that should give us 0.81. 0.8124. All right, so that's it. Anybody with any question? If you have a question, you can let me know. If you have any question, let me know. You are disturbing the class. I told you that if you have a discussion to do or something, you should know how to put that. Although you're in class, you're not supposed to be discussing. All right. Any question? Hello?
No question, sir.
Okay. If you say there's no question, then we can continue. We'll have a few more minutes to make up for. Now, what are the other things that you should be aware of? Now, the binomial distribution, as well as the Bernoulli distribution, okay, has a mean and variance. All right?
Yes, sir.
Okay. Now, we will need to look at those mean and variance, but apart from that, we look at some other, okay, yeah, mean and variance specifically, but you need to be aware also of the third stuff that we'll look at now. So let's just quickly put it together. Sorry, mean and variance of the binomial distribution. Now, the mean of the binomial distribution is capital E of X, from what we said before, and that will be n multiplied by t. Now, I would like to put something else. The second moment about the origin, it also has a value, but let's leave that for now. The variance of X is equal to NP multiplied by 1 over P, rather 1 minus P rather. Now, some of you may come across situations where they write N combination, okay, sorry, N multiplied P and like NPQ. Now, if you come across that, then it means that this is equal to 1 minus P, Q is equal to 1 minus P. But I would rather that you specify it this way for ease. And then you are aware of the fact that f of x is equal to all of what we have said it is equal to from here. So if I ask you for the properties of a binomial distribution, or you are asked anywhere that what are the properties of a binomial distribution, then by stating all of what I'll be stating here, I've not done stating, I still have one more. Then you have given me the properties. And this one should be P. All right, now there are ways of establishing these arguments, or rather what I have here, but we will not be doing that. It will take a long time. So we will not be doing that. And it's beyond what your course requires at this time. So what about the mean and variance of your Bernoulli distribution? I'm particularly interested in this. Somebody who is really observative should be able to give me the properties. All right, so number one, Bernoulli distribution, that's what we're looking at now, not binomial again. Bernoulli. Who can state the first one?
The mean will be P. The mean will be P.
The mean will be P. Okay.
Because it is conducted once.
Yes, that's correct. Equals to P. All right. The next one.
The next one.
It will also be P.
It will also be P.
Yes.
So is that mean square like that? Is that EX means
No.
square?
You don't seem to get something here. Do you remember that we said something like expected value of X? I mean variance of X rather.
Yes, sir.
Equal to the expected value of X X squared, expected value of X squared minus in square bracket now, the expected value of X
all square.
You remember that? Now,
yes,
what we are talking about here, the expected value of X squared we're talking about here is this one.
Yes, I mean, what is, yes, I know the expected value of X equals to the mean. So what is the name we can call that EX square?
This one?
Yes, sir.
Is
yes,
the second moment about the origin. It doesn't have any other name. Second moment. This is called, we just call this one mathematical expectation, but what you are seeing here is actually called, referred to as the first moment about the origin. That's what we call expected value of X minus 0. About the origin means 0.
Okay, sir.
So we had R here. So when R is 1, it is called the first moment about the origin. When R is 2, it is called the second moment about the origin. Usually, we don't like to write this that way. We like to write it like this because the 0 thing scares some people. So we prepare to write it this way. All right? So when R is 1,
yes,
it's called mathematical expectation or the mean.
That's the first origin.
When R is 2, it is called the second moment about the mean. About the origin, rather.
Okay,
second moment about the origin. So you don't need all of these ones here. Just need to be aware of them. All right. Now,
variance.
What will be the variance?
Straight PQ.
The variance will be
PQ
equal to P. I said I don't want to use Q because we have not defined Q anyway. So please, if you ever write PQ for me or for anybody, as long as you're talking about mathematics, you must do this. So I like to save my space, so I prepare to write it straight away. If you write PQ without having to specify what Q is, then you have done nothing because we don't know where Q is coming from. I won't take that from you, and nobody is going to take that from you mathematically. All right. Now, f of x, the fourth one says f of x. Well, when we did it the other time, we did it together, but I want to know something. You may write it in such a way that it is written as p raised to the power of x, 1 minus p raised to the power of n, and 1 minus x, x equals to 0, x takes value from 0 to 1. Or you may write it like this, f of x equals to p Okay, we'll need to have curly bracket. So p raised to the power of x, where x is equals to 1, or 1 minus p raised to the power of 1 minus x. So, and in this case, it doesn't have to be, you may just don't even need to write anything there. But let's just put it, no. When x is 0, when x is 1, this becomes 0. So when x is 0, so there's no need to write that. You may not put 1 minus p in bracket if you like. So when x is 0, this does not have to be there. So if you do the calculation, I mean, you do just put 0 here. When you put 0 in this equation you have now, you put 0 here, it will become p raised to the power of 0, that will be 1. Put 0 here, you have 1 minus p. That is the case for when x is equals to 0. That's why we have 1 minus p there. But if you put 1 here, you are going to have p, and put 1 here, everything here becomes raised to the power of 0, and that will be 1. That's why you have p here in this case. So if you write your f of x for a Bernoulli distribution rather, you write it like this, you are correct. And if you write it like this, the one above, you are also correct. Okay?
Yes, sir.
Okay, but it's easier to remember this one. So I would advise that you use this because you can remember it in conjunction with the binomial distribution. All right, so that's the word here now, this or this. So whichever one you prefer to use. So those are the properties of your binomial and Bernoulli distribution. And that being said, we are done with the binomial and Bernoulli distribution. Now, but before we go, I want you to be aware of certain things. If I ask you that, what are the conditions for your binomial distribution and binomial experiment or Bernoulli experiment, then you will need to tell me certain things that I have written here. I wrote a number of them, but please take note of them. Some of you may not really have paid attention to them, so I will emphasize a little on them again. It's not just me asking you, you need to know what you're doing so that you can use it anywhere. Conditions for a Bernoulli experiment. Number 1, the experiment is conducted once. There are only 2 possible outcomes. Okay?
Yes, sir.
Okay, so those are your conditions. And then the next one is that your P, the P is the probability of success. So, okay, you may have this as your 4 conditions. If you check your courseware, you are likely to find 3 there, but I've given you 4. So take note of all 4. They are very important. So experiment is conducted once. There are 2 possible outcomes, only 2 possible outcomes. The random experiment, the random variable of interest is the number of successes observed, and then the probability of success is P. All right. But for your binomial experiment, if you are asked what are the inclusions, what are the conditions for the binomial distribution or binomial experiment now, you are going to have the random experiment is performed at least once. You have that. There are only 2 possible outcomes also. I've given you examples of outcomes. The random variable of interest is the number of successes. The probability of success is P, and the probability of failure is 1 minus P. Then the last thing you must note is that each trial of the experiment is independent of the other. So please take note of those. I've said that now because some of you will not take note of that, and then you just do whatever you like, and then so that will not be okay. So that's why I'm taking time to go through it again. If you are now asked for the properties of your binomial distribution, Okay. You may go ahead to give those things I've written on the board earlier. But for the binomial distribution, there are a number of things that you can add or you should add. So we'll go back there, round up the session with that. Now for your binomial distribution, you should also be able to tell me. So that will lead us to number 5, and that the number of trials are independent. So rather than calling this mean and variance, I think we should just rename this to properties of the binomial distribution. This will also be properties of the Bernoulli distribution. So I'm saying now that you need to know that the number of trials are independent. Right, and then you also need to know all right, I think all you need to know there is okay, we may add one more. I know these are part of the conditions we dealt with when we were dealing with say condition for binomial experiment and that, but you can include them. The probability of success is P, and the probability of failure is 1 minus P. So if you're able to state this, you have done well concerning your binomial distribution. So that's that about that. Okay. So you may say each trial, rather than the number of trials are independent, each trial is independent of the other. Each trial is independent of the other. So you may put them together if you like. There are n trials, and each trial is independent of the other. So that's that about that. All right, you can read your courseware to find out some other stuff there, but just know how to put your answer if you are asked this, or if you need to apply this, know what you are doing. So that's that about that. Any question?
No questions, sir.
All right. If you have no question, I have a question, and somebody will have to do that.
Okay, sir.
For the case we considered earlier, now suppose that we have a man and his wife, like they are about to give birth and they want 5 children, and then the probability of having a male child is 0.5. Then we can find the mean and the variance for the number of male children. So from the question, n is 5. So that's because we're told that they want only 5 children. P is 0.5. That's because we were told that the probability of having a male child is 0.5. And since we are concerned with the male child, then we can find the mean by doing all of this. We know 1 minus P is also 0.5 from here. So we'll just fix that. This will be the mean. So we'll fix the parameters we have here and we get 2.5. As well as we can also find the variance, and the variance will be defined as this. So just fix the numbers we have here, the parameters we have in here, and then we get 1.25. Now this one in red has nothing to do with our question here. So I just want to use this to illustrate that you may not have P to be equal to 1 minus P all the time. So in a situation where P is 0.3, for instance, P will not be the same thing as 1 minus P. And your variance of X, if your N is defined as, your N is 5, let's assume you're doing the experiment 5 times, you will have your variance to be something like this. And your NP, that's the mean here, would have been 0.3. I mean 5 times 0.3. So that's, I think that illustrates the principle of mean and variance of the binomial distribution. You should be able to do that of the Bernoulli distribution. You already know that you will not have n there. N is 1. So when you see that of the Bernoulli distribution, you should be able to differentiate. All right, so at this point, it's sufficient to bring the class to a close. And I don't know if somebody wants to get anything, you want to hear anything or know anything. Perhaps there's something you did not, that was not touched well today or something. Hello?
Hi, sir.
Any question?
Yes.
Okay. Any question?
Everything went well, sir. Everything went well. No question, sir.
All right, no question. Okay, thank you. So